Okay, so we're going to continue with chapter 5. I'm going to jump here back to my my little screen. If I can get the camera to cooperate. There we go. For some reason, as soon as I get here, my mouse pad stops wanting to cooperate. There we go. All right. When we left off, we were talking about a laboratory test that had components of fixed cost components consisting of 50,000 in salaries and 50,000 in lease expenses for a total of 100,000 in fixed costs. And then we said that for each unit, each test that they did, there would be $10 in reagent costs. Okay, so this is called the underlying cost structure. Right, this is the cost structure, and it is the component, and it is the total cost is equal to the fixed cost plus the variable cost per unit times the quantity produced. Okay, so there's a fixed cost component that basically is the cost of starting up the business regardless of the volume that we do. And then there is a variable cost component that increases as we increase the volume that we are doing. And I'm sorry, back row. Don't know names. Hello? Okay. Okay, so let me demo. I'm going to go ahead and demo this using Excel. Just because it's faster for me since we're on the computer anyway. Okay. So we're going to program in our cost structure. And I'd like you to, this is kind of a dual function here. I want to demonstrate some of the capability of Excel in case you haven't used it. It's pretty simple stuff. So let's assume that we do one, actually let's start with 0. And I will post this spreadsheet so you can have it. Feel free to write it down too, but I will post it so you can have it. So in our example, we're doing 0 volume, meaning they're not going to do any tests. What is the fixed cost incurred by the organization? Based on what we just talked about. It's 100,000, right? They hire the employee and they rent the equipment. So the fixed cost is going to be 100,000. The variable cost is directly driven by the number of tests done, right? So for every test, we incur a $10 cost, a $10 variable cost. So what we're going to do is we're going to say equals 10 times the volume, right? So I'm just programming into that cell. So when you do a formula in Excel, you start with the equals sign, then you can program in you can type in an absolute value like 10 or 47 or 100,000 as I did over here. The asterisk is the multiplication symbol in Excel. And then you can, using your cursor, choose a cell to have Excel reference. So in this case, it's saying 10 times whatever is in A3. Now the way we navigate Excel is we look at the column, the letter of the column, and the number of the row. So A3 refers to column A, cell, or row 3, and so we get A3 here. This would be B3, right? This cell here would be B3. This cell here, where VC is, would be C2, right? Which I didn't mean to do. All right, clear that. I'm going to go back and choose A3. So what this is going to do is it's going to say 10 times whatever the value in A3 is. And since the value in A3 is 0, we're going to wind up with 0. Now I want the total cost. The total cost is the sum of the fixed cost plus the total variable cost for the given quantity. So all I'm going to do is I'm going to say equals 100,000 plus my variable cost. Now, oh, hey, it's 100,000. These lines are not going to be meaningful yet, but these are going to stand for average total cost, average fixed cost, and average variable cost. And so because we would be dividing by 0, we'd wind up with errors in those lines. So I'm going to go down here. So actually, I want that to be. Okay, so that's kind of our starting point. What if we do one visit? What is the fixed cost going to be? We've hired the technician and we've rented the piece of equipment, right? The technician has shown up to work and we say, technician, do one test today. The technician makes, what is he making? 50,000 a year, so he's making $25 an hour. So he works an 8-hour day. 8 times 25 is 200, right? So he expects to be paid his $200 at the end of the day, whether he does 0 tests, 1 test, or 1,000 tests, right? He says, hey, boss, you owe me 200 bucks, right? So if we do that over the course of a year, he keeps showing up and he keeps expecting to be paid $200 a day, right? And so that adds up at the end of the year to $50,000. The people that we're renting the equipment from don't really care how many tests we do. They just say, hey, the payment is due, it's $50,000, right? So if we do one test, what's the fixed cost? It's 100,000 again, right? It doesn't change, that's the point. All right, how about the variable cost? It's $10 per unit. What's our total variable cost if we do one test? 10, right? 10 times 1, 10. And then our total cost is going to be 100,000 plus 10, 100,000 and $10, right? So I just copied, what I just did was I copied the formula, well, I copied the actual 100,000 down. I copied the formulas down here. And here's something I want to show you. Remember above here, it was 10 times A3. In Excel, if I copy the formulas down to the next set of cells, it automatically updates the references. So I was referencing A3, I copied it down 1, so now it's going to reference down 1 row, or A4, right here. And then this one was B3 plus C3. I copied the formula down 1 row. It updated it, so now it's saying, give me B4 plus C4, right? Okay, so that's the Excel part of this. All right, average total cost. So I want to know the average total cost per unit. How am I going to get that? So I have the total cost, I have the number of units. What am I going to do to get the average total cost?
Would you take total cost and divide it by volume?
Yes, I'm going to take my total cost. So I'm going to say equals, and I'm going to choose the total cost value, and I'm going to divide it by the volume, which in this case is 1. So 100,010 divided by 1 is going to be 100,010, right? The average fixed cost. So now I want, instead of just, I don't want to just look at the average total cost. I want to look at the average fixed cost. What am I going to do to get the average fixed costs? Well, average total cost was total cost divided by volume. How about average fixed cost? What do you think, Chloe? Fixed cost divided by volume. Very good. So I'm going to take my fixed costs divided by my volume. Okay, so B4, I'm going to take fixed costs divided by volume, and oh, hey, it's going to be 100,000. So these are kind of uninteresting findings at this point, right? Because we're dividing by 1. Don't worry, it gets really exciting in a minute. That's a finance joke. Okay, so average variable cost then, all right, is just going to be variable cost divided by volume. So at 1, it's going to cost us, it's going to cost the lab $100,010 to do 1 test. That's a really expensive test, right? So what we want to do is take advantage of what's called economies of scale. Okay, economies of scale means that if we do high volumes, we can reduce our average costs down. Okay, so I'm going to demonstrate that. So I'm going to start jumping the volume up. So instead of doing 1 test, I do 10 tests. And here I'm going to just copy these formulas down. Stop it. So at 1 test, my fixed costs are still the same, right? Because my fixed costs are fixed. They don't change based on the volume within the relevant range. We talked about that last time, right? And we said the relevant range for this was going to be 20,000 tests. So up to 20,000 tests, those fixed costs don't change. So when we go from doing 0 to 1, we go from $100,000 to $100,010. When we go up to 10 tests, we still have a fixed cost of 100,000, but we now have variable costs of 100. So our total cost is 100,100. Our average total cost is going to be 100,100 divided by 10, the volume. That gives us an average cost of $10,010 per test. Still a really expensive test, right? Like, you're not going to pay $10,000 for a test unless you know that if you don't get the answer from that test, you're going to die. Right? That's the kind of cost, right? We're talking about, hey, you can have an inexpensive new car, or or a new to you car, or you can have this test. Like, that's a lot of money. We don't want to spend $10,000 on a test. So let's jump up to 100. Well, what changes? Fixed cost at 100 is, everybody now, 100,000, right? Stay with me. Okay, variable cost is going to be $10 per unit, so 10 times 100 is 1,000. Okay, all right, yeah, it's 8 o'clock, I got it. Good. So now we see fixed cost, still 100,000. Variable cost, now 1,000, right? 100 times 10, 1,000. Our total costs, 101,000. Look what's happening over here to average total cost, though. We went from average total cost of 100,010 to 10,010 to 1,010. All right, now we're starting to, now we're starting to get a little more reasonable. Oh, I forgot to say. Okay, so over here, average fixed costs. When we did 1, it was 100,000. When we did 10, it was 10,000. When we did 1,000, 100, it's 1,000. So that's pretty good, right? Average fixed cost is falling as we increase our volume. But the fixed cost isn't actually changing, right? The fixed cost is still the fixed cost. So what's going on there? Well, mathematically, it's pretty straightforward, right? Caitlin, what's happening? Right. So what I'm doing, Caitlin said, we're dividing it by how many we're doing. Exactly. So mathematically, as I increase volume, average fixed cost is going to continue to fall. From a managerial perspective, what does that tell you? What's going on in your organization? You've got this big fixed cost, right? And as you increase volume, you are spreading that fixed cost over more units produced. So this is what economies of scale is, right? Is your fixed costs are fixed, so they're going to be whatever they're going to be. If you can do more stuff with those fixed costs, what you're doing is you're driving down the average fixed cost. You guys that are watching from home, you don't get to see me waving my hands around, okay? But trust me, I'm waving my hands around very expressively. Okay, so now we're going to go to, we'll jump to 1,000 units. So at 1,000 units, what's my fixed cost going to be? 100,000. Thank you, Krista. Right? At 1,000, my variable cost, 1,000 times 10, 10,000. My total costs have now gone from 100,000 to 110,000. But check this out. My average total cost has gone from 100,010 to 10,010 to 1,010 to 110. Right? So my average total cost, if I do 1,000 tests over the course of this year, on average, it's going to cost me $110 to do it. How much can I charge for this test? If I do 1,000, what's the minimum I would have to charge for this test? What's your intuition tell you? 110, right? I want to at least, if I'm going to do something, right, I don't want to lose money on each thing I do. I want to at least break even. So my break even here would be $110 per test, right? Still pretty expensive if this is something super simple, like, you know, hey, let me get a blood sugar measure or a, you know, or a CBC count or something like that, right? These are not things that people want to pay $110. So let's jump to 10,000, right? So we said we could do up to, 20,000 tests. So if we jump now to 10,000 tests, so at 1,000 tests, that's not a lot of work for our lab technician, right? He's kind of sitting around spending a lot of time playing Animal Crossing in between tests or something like that. You guys play Animal Crossing? Yeah, all right. My daughter is like a total addict on Animal Crossing. She tries to explain like she's got to go fishing to do this or, you know, to build her house, and I'm like, all right. She also watches TikTok, and I totally don't get any of the TikTok humor. And she's like, look at this, it's hilarious. And I'm like, don't get it. You guys are just, it truly, like, that's a generation. Like, TikTok to me is like the first time I truly feel disconnected from your generation. Like, I don't get it. They don't make me laugh. There's just like a lot of screaming involved, and I don't know. I don't understand. Anyway, so now we've done 10,000 tests. We're about halfway to our capacity. And now look at what's happening. The average total cost has fallen from 100,010 to $20 per unit. So at 1,000, we would have had to charge $110. If we can get our volume up to 10,000, we can charge our customers $20. How about our average fixed cost? Well, our average fixed cost has fallen from 100,000 to 10,000 to 1,000 to 100 to now 10. What about our average variable cost? It's not changing, right? We could build something that would change a little bit, but it's not changing. This is a very super simple model. So the average variable cost stays at 10, right? So the economies of scale come from the ability to spread the fixed cost over greater volume. So now let's max out our technician, max out our machine, push it up to that 20,000 limit. What's our fixed cost? Well, hey, it's still 100,000, right? Because we are still within our relevant range. The machine can run 20,000 tests a year, and the technician can run the 20,000. So with one technician and one machine, we can run 20,000 tests, right? So our fixed costs still are 100,000. Our variable costs are 200,000 because that's 20,000 times 10, because our variable cost is not changing. It stays $10 per unit. So we now have our variable cost is now exceeding, I should have made that point earlier, at 10,000, our variable cost and our fixed costs are equal. At 20,000, our variable costs exceed our fixed costs. So now we have a total cost of 300,000 for this operation, which is a lot of money, right? Relative to the 100,000 we had when we just opened the doors. But if we look at it, we have now driven our costs down, our average total cost down, from $110 for one unit to $15 per unit for 20, if we can push ourselves up to 20,000. So this is, again, a demonstration of this idea of economies of scale, right? So when you think about like modern manufacturing processes, if you ever see like a picture of an assembly line of cars, right? They're pushing these cars through super fast. And now today, you know, it used to be people would be on either side. Now just robots are like putting things on the car, right? Lots and lots of fixed cost. A factory of that type is super expensive. So to make it effective, you've got to push through a lot of volume, right? A lot of volume has to go through there. When you can push through a lot of volume, you can sell that stuff for super cheap, right? So, you know, you'll get your, I mean, relatively speaking for a car, right? I mean, cars are still a lot of money. But if you compare, like, the reason that a Ford Fiesta costs, you know, what, $15,000 and a Lamborghini costs $300,000 is Ford has high fixed costs, right? But they do a very high volume. So they have this very expensive factory, big factory, and it's very expensive. So they have very high fixed costs, but they run tons of volume through it, right? And so that drives down the average cost per unit because it drives down the fixed costs per unit way down. Lamborghinis are handmade, right? They're like, there's like a group of Italian guys. There's Luigi and Fernando, and you know, and they're all like, hey, you know, they're making the Lamborghini. Let's make the Lamborghini, you know. And so I can see that, I'm Italian. So, you know, hey, let's make the Lamborghini, you know. And then they go home and they make the pasta, right? So they come to work, they make the Lamborghini. And right, but it's all variable cost because it's all people, right, going through and making it. So Lamborghini is not an assembly line thing. They don't have I mean, they still have some high fixed costs, but relatively speaking, they're not pushing through a lot of volume, right? I don't know what the volume of Lamborghinis is, but it's tiny compared to Ford Fiestas, right? Ford, tons and tons of throughput drives down the average fixed cost. Lamborghini, very small throughput, very high variable costs, right? Very high variable costs. They don't get economies of scale. And there's a whole, like, we can talk about the marketing behind that, and, you know, why is it that they can get away with charging $300,000 for a car? You know, but that's the separate story. So the big story that we want to pay attention to here is the average fixed costs and the average total costs and the average variable costs. What you can see is the average variable cost stays constant in this very simple model, right? It's always 10. It's 10 for one, it's 10 for 20,000 per, right? We're talking the average. The average total cost falls continuously as long as we are within the relevant range, right? We don't have to add new equipment, we don't have to add new personnel. As long as we're within the relevant range, if we can drive out or drive in more volume, right, and fully utilize the resources that we have invested in, if we can push toward that top end 20,000 limit, then we squeeze out all the inefficiencies of our operation, and we can reduce cost from extraordinarily expensive to quite inexpensive, right? And the gains or the reductions in this model are all coming from an increase in volume while holding our fixed costs constant, right? So the total fixed cost never changes, but because we are dividing total fixed cost by an increasing volume, we get a smaller and smaller average fixed cost. And that's super exciting, right? So that's our demo there. Save that real quick. So we demoed that. So the cost structure is important. And why is it important? Because we can understand then how we're going to drive down the cost per unit, because we want to produce as inexpensively as possible. Let me graphically represent what we've been talking about here now. So if we have dollars in cost and volume on the bottom, or quantity, I'm sorry, I keep going back and forth between volume and quantity, but let's say volume for now. But volume, quantity, same thing, right? If I've got a variable cost per unit of $10, and I do, 1 unit, it's going to be $10, right? If I do 100 units, we just did this. If we do 100 units, it's going to be $1,000. If I do 10,000 units, right, it's going to be $100,000. And if I do 20,000 units, it's going to be, I'm trying to draw a straight line. Right, it's going to be 200,000. So I could draw a sort of straight line based on my dots, right? What's the slope of that line going to be? What is slope? Talk about in math, I'm talking about slope. MX plus B. Good. All right, Emma, thank you. So Emma actually gives us the formula for the line, which is MX plus B, right? So in this case, so that would be the formula for this line. So the formula for this line, if we are doing, this is pure variable cost. So we're only graphing the variable cost. So there is no, B is 0 in this case, right? Because if I do 0 visits, or if I do 0 tests, I have 0 cost. So there is no B. If volume is my X, right, then what must M be in this case?
10.
10, right? 10X plus 0, right? So the dollar amount, right, in this case, my total variable cost is equal to 10X. So the slope, this is how we indicate slope for a line, is this little like right angle triangle coming off of it, is going to be 10. So that tells me, the slope gives me an idea of how steep is my curve, right? Or my line in this case, it's a straight line. If I instead had a variable cost per unit of say 20, what would happen to my line? Would it be shallower or steeper? It's going to be steeper, right? Because if this was our 10 value, at 10 with a slope of 10, I'm going to be at 100. If I have a slope of 20, at 10, I'm going to be at 200, right? If I had a slope of variable cost per unit of 30, even more steep, right? Going to be like this. And these are not, to scale. But at a slope of, at a volume of 10, if I have a variable cost per unit of 30, I'm going to have total cost of 300. Right? So if this is just my variable cost I'm measuring, right? Total variable cost, dollars total variable cost. The lines all come out of the origin, regardless of what the variable cost is, because when I do 0, my variable cost is 0, right? And then depending on what the variable cost per unit is, depends on how steep the line is going to be. So I'm graphically representing my costs. The higher my variable cost is, the steeper that line representing variable cost is going to be. How about fixed cost? Call it total fixed cost or just fixed cost because it's not like it's changing. So if I graph my fixed cost from our problem from before, what's that line going to look like? I just graph fixed costs. I ignore my variable costs. We said that fixed costs, right? Our cost structure was 100,000 plus 10Q. So if I just want to graph, okay, Emma says a straight line. Okay, Emma, but this is a straight line too. So when you say straight line, what do you mean? Horizontal, good. It's going to be a horizontal line. And it's going to equal $100,000, right? Why is it a horizontal line? Because at 0, my fixed cost is 100,000. At 10, my fixed cost is 100,000. At 100, my fixed cost is 100,000. At 1,000, my fixed cost is 100,000. Right? So on all the way out. Doesn't change because it is independent of it is independent of the volume. Trying to see the chat. MX plus 3 straight line. Okay, good. Okay, so we've got this straight line fixed cost, this horizontal line fixed cost, this increasing line for our variable costs. So now I want to do total cost. I want to graph the total cost of my process. But we said earlier, total cost is fixed cost plus variable cost times quantity, right? That's B plus MX. So if I graph that, I'm going to want to start, so this is dollars total cost. This is my volume or quantity, either one. So I'm going to graph this now. What's my B value? It's my fixed cost, so how much is that? 100,000. And then my MXQ is, or MXV or VC, whatever, is 10Q, right? So graphically, what is this going to look like? Well, if it doesn't jump out at you immediately, plug in numbers, right? This is a good process. So if I get 0, what's my volume, my value? What's my Y value? This is the Y-axis, this is the X-axis, remember that? At 0, how much total cost do I have? 100,000, right? And then let's say at 1,000, I have a total cost of we just did it. Same numbers as before. At 1,000, we have a total cost of, oh, the thing just jumped for me just all by itself. So at 1,000, oh, that's because I fell offline, I think. No, I didn't. So at 1,000, we're going to have 100,000 in fixed costs, 10,000 variable costs for a total of 110,000. Right. At 1,000, I'm going to have some value like that. At 10,000, I'm gonna have some value like that, right? At 10,000, I've got 100,000 in fixed costs and 10,000 times 10, 100,000 in variable costs, so a total of 200,000, right? At 20,000, 1K, 10K, 20K, right? I know this isn't proportionate. I now have, right, 200,000, 20,000 times 10, 200,000 in variable costs, 100,000 in fixed costs for a total of 300,000. So I wind up with a line that looks something like this. I know it's not to scale. Where I have a fixed cost component equal to 100,000 and it doesn't change, right? And then I have this total cost line going up with a slope of 10. It starts at 100,000, right? It starts at the B value, which is the y-intercept. If you remember that phrase, it's the y-intercept. Starts at 100,000 and then goes up from there. So it starts at fixed cost of 100 and then just goes up. What's this gap between total cost and fixed cost? What's the difference? The variable cost, the total variable cost. Because total cost is equal to fixed cost plus total variable cost. If you look here, right, this is my total variable cost. Variable cost times the quantity is my total variable cost at any given quantity. Now that number changes depending on the quantity, right? So the key here is to remember that the fixed cost kind of sets my baseline, and then as I add additional quantity, right, my total costs keep going up. Now, what happens if we want to go past 20,000, our relevant range? What has to happen? Well, we said before, why is 20,000 the relevant range? Well, the machine is capable of running 20,000 tests if we run an 8-hour shift with one technician, right? So if we want to do more than 20,000 tests, there isn't enough time in the day for one technician to run 20,000 tests. So what do we have to do? If we want to go past 20,000, if we want to do 20,000 in one test, what do we have to do? Hire more, says Emma. Right, exactly. So that's one option, is we could hire a second tech and they could run a second shift, assuming that the machine can run, you know, that the limit isn't the machine, but the time of the day. You could add a second tech. The second tech costs $50,000, so we tag on a second tech with a second shift, right? So tech number 1 comes in, works 8 hours. Tech number 2 comes in, tech number 1 goes home, tech number 2 comes in, runs another 8-hour shift. That could work, and you'd have 20,000 additional tests. An alternative could be that maybe it's not so much the technicians, that's the rate setting limit, but the machine itself. Maybe, you know, maybe all that's really involved is the tech loads the machine and then sits there and waits for the thing to be done. So maybe if we bought a second machine, the tech could run 2 machines simultaneously. So load up one, turn it on, turn the other one, load up the second one, turn it on. And then when that's done, it takes stuff out of machine 1. So you could, I mean, that may or may not be true, right? It might be that the tech really needs to work continuously to sustain that flow. It kind of depends on what you're, you know, it depends on the specifics. Probably the simplest example would be what Emma said, which is to hire a second technician. Fixed cost, yeah, add a machine, good. So what would happen at 20,000 is our fixed costs would jump from 100,000 to 150,000. right? Fixed cost equal 150, starting at 20,000. And so we would see a commensurate jump of 50,000 in total costs at 20,000. And then we would continue happily on our way with total cost still increasing at 10 per unit. Demo that. So if we want to go to 20,001, our fixed costs are now 150, right? And so suddenly we now jump total cost from 300 to 350. Our average total cost is low, but more than it was. Our average fixed cost spikes back up. If we are able to push that to say 30,000 tests though, right? We push our cost per test back down. If we can push all the way up to our maximum 40,000, we can actually achieve even lower average total costs of 14 per unit. Why is that? Because while we added 50,000 in costs, right? In fixed costs, our variable costs stayed the same, and so we were able to spread a slightly larger amount of fixed costs over an even, over twice as much volume. So that's what happens. You will be making those kinds of decisions when you go into the real world. All right. Let me give you an example to work on for a second. Imagine you are running a family practice clinic, and they have $5,000 in rent and $30,000 is per month. 30,000 in salaries, and supply costs on average are $15 per visit. What is the underlying cost structure for our family practice clinic? Give you a second to think about it. They paid $5,000 in rent per month. They pay $30,000 in salaries per month. And they, on average, spend $15 per visit on supplies. So if I'm going to build if I'm going to try to build a model of their cost structure, their underlying cost structure, what's it going to be? Chloe, looks like maybe you have it. What do you think? Good. So Chloe says TC equals 35,000 plus 15Q. 35,000 plus 15Q. Good. Because the 5K in rent and the 30,000 in salaries is what kind of cost? Fixed cost, right? And then this represents our variable cost per unit. That's a super simplified model. And you could argue, well, salaries could be variable. Well, sure, yeah, it could be. In the long enough run, we could make them variable, or we could, or we could put our staff on some sort of commission basis, so that that we tell them, hey, you're paid by volume, right? You're paid piecework. So if we see lots of patients, you get paid a lot. If we see few patients, you get paid very little. Most staff don't want to work like that. You don't want, most of you probably, jobs you work in don't get paid on a commission basis. You might get some tips, but depending on if you're a waitress or something. But mostly if you're working in retail or something like that, you're not working on a commission. You show up, you get $12 an hour, and you go home. Right. So most staff in a healthcare organization are not on a per unit, paid on a per unit basis. They're paid on a salary basis. Okay. So what would be if we drew this up real quick, we got our volume, we got our fixed costs, total variable costs, and total cost. If we had a volume of 1, we had a volume of 100, 500, and 1,000. Work out your numbers real quick for that. And give me an average total cost too, while we're at it. Average total cost is really important because it tells you how much you have to charge per unit in order to make a profit, right? On average. Start with 1. Fixed cost for 1. How much? Fixed cost for 1 would be 35,000, right? Let me just use K. Total variable cost for 1. What's the variable cost? 15, right? We're doing one. It's going to cost us $15. So the total cost is going to be and so the average total cost is going to be right, because I'm taking that total cost and dividing it by 1. All right. If we do 100, what's the fixed cost? $35,000, right? Total variable cost. Well, it's a 15 times Q, 15 times 100. Not sure what's happening here. My keypad is not like this. Good. 15 times 100, 1,500, right? Total cost is 35,000 plus 1,500, 36,500. Average total cost is 36,500 divided by 100. Well, if you divide by 100, you can just take off 2 zeros. That's a cute trick I learned a long time ago. So you get 365. I do 500, what's my fixed cost? 35,000. My total variable cost, 15 times 500, 7,500. Total cost, 35 plus 75, 42.5. Average total cost, 42.5 divided by 500, that's 85. So notice how my average total cost is falling. It's really expensive to just do one, right? Super expensive to do 100, but we get down to 500, we're getting into the reasonable range. Fixed cost for 1,000 visits. 35,000, good. Yeah, you get into that, whatever. All right, so total variable cost, 15 times 1,000, that's 15,000. Total cost, 15 plus 35, that's 50. 50,000 divided by 1,000, you just lop off 3 zeros, that gives you 50. So what you could see here is as they increased their volume, they better spread their fixed costs. They accomplish economies of scale, and they take better advantage of their fixed costs. And as a result, with a lower average total cost, they can charge a lower amount, which is why Walmart can charge so little for things that, you know, and why they wiped out. I mean, I know they wiped out all the mom and pop stores before you guys were born. But back in the day, we had these expensive department stores in, you know, small towns. And then Walmart rolled in, and with its massive fixed cost, but its massive volume, it was able to drive down its average total cost way below what the mom and pop stores could do. Mom and pop stores had a much lower fixed cost, but a much higher variable cost per unit. With Walmart buying on massive volume, they were able, even though they had a very, very high fixed cost, they were able to spread that fixed cost across many stores and many communities, and that allows them to drive down their average total cost. Walmart has huge economies of scale, and that's why they can sell you all that crap for so little money. Right? And that's true of any large business. Walmart just illustrates it well. Okay, so we've talked about cost so far. Now we need to talk about revenues, because cost is only 1/2 of the profit function. And we really don't just care about cost, we also care about profit. Not sure why my thing is so. So we'll start by talking about revenue under a fixed, fee for service approach. And I'm going to abbreviate that FFS, okay? Fee for service. What does that mean? I walk into the doctor's office. I say, doctor, I don't feel good. Doctor says, okay, sit down. Pokes and prods me, says, you have, the common cold. Take 2 aspirin and, go home. And then as I walk out the door, they hand me a bill for $100, right? That's fee for service. The alternative to that, kind of the extreme alternative to that, is capitation. And you should be familiar with these ideas, but I'm just going to refresh you on them, right? So we have capitation. Capitation is this is a revenue per unit of service. Capitation operates on revenue per covered life. So whereas the fee-for-service is by far the dominant model in our economy, in our healthcare economy, by far the dominant model. Patient comes in, gets a service, gets a bill for that service. That's fee-for-service, right? Capitation is increasingly represented, is kind of in some sense the ideal. Some organizations operate on it. You guys have read about Kaiser Permanente, for example. If you are a Kaiser Permanente buyer, right? So you're covered if you have your insurance from Kaiser Permanente. It's an HMO, right? You pay some fixed amount of money per month. You go in, and they provide you all of your care for that fixed amount of money. You don't pay anything else. You might pay a small copay, but for that fixed dollar amount, they provide you all your care. Right? So if you pay $1,000 a month in health insurance, and they cover all of your costs, and they don't bill you on a per service basis. When an organization agrees to capitated reimbursement, what I'm saying, so if UNH contracted with Wentworth Douglas, for example, to provide care on a capitated basis for the UNH faculty, for example, they would say, okay, Wentworth Douglas, we're going to pay you a fixed dollar amount per faculty member. We're going to give you $100 a month per faculty member, $500, whatever. And for that $100 per month or $500 per month or $25, whatever the number is, that's called a per member per month, or PMPM, per member per month, or PMPM. And we'll come back to that a little in a minute. I'm going to do the fee for service first, but I'll talk about this. On a PMPM basis, they're going to say, hey, I'm going to give you that amount of money. And for that amount of money, you're going to take care of all of my employees, all the faculty, right? So I'm going to give you $100 a month. There's 5,000 faculty or whatever we are. I don't know. It's not that many. So 5,000 times $100 per month, you're going to get $500,000 per month. And you have to provide all of the care for all of the faculty for that $500,000 per month. Caitlin's on faculty, and Deb's on faculty, and Chloe's on faculty, right? So you got Professor Deb and Professor Chloe and Professor Caitlin, right? If Caitlin doesn't get sick, she's super healthy, she never gets sick, right? Then they get the $100 per month, and they don't have to provide her any care. Deb never gets sick, they get $100 per month for Deb. They get to keep that money, right? Chloe never gets sick, they get to keep Chloe's money. I, however, fat old dude, right, get sick all the time. They have to pay for all of my care. They have to pay for my primary care. They have to pay for my specialty visits, right? I go, oh, my knee hurts. Oh, my back hurts, right? Oh, I've got some weird pain in my belly, all that stuff. They got to pay for all of that out of that $100, and they don't get any more money. Right? They don't get to send a bill over to say, hey, Bonica showed up again. Here's another bill. No. And UNH says, no, we agreed. we're going to give you $100 per month for all of our faculty, right? And you get to, if you can provide the care for less than that amount of money, then you win. But if it goes, but if the cost of the care goes above that amount of money, then, you know, don't call us, we won't call you. Okay, so that's capitation. All right, we're going to focus on fee-for-service first. And we're going to model fee-for-service. So when we model fee-for-service, we're going to have some fixed dollar amount that we charge per unit. It's going to be a charge per unit or a revenue per unit. So let's go back to our lab example. Let's assume we can charge $50 for a lab test, right? So if we set our price at $50 for a lab test, if our lab test is $50 per test, then we're going to take 50 times our volume. So in this case, if I do 0 tests, I get 0 revenue, right? And then I could just copy that down. If I do 1 test, I get 1 times 50, that's $50. If I do 10 tests, that's 10 times 50, $500. If I do 100 tests, it's 100 times 50, $5,000. If I do 1,000 tests, it's 50 times 1,000, $50,000. 10,000 tests, I get 500,000. 20,000 tests, I get $1 million. Right? Yay. Doing good. So what does that look like graphically? Total revenue is equal to price times quantity, P times Q. Right? So if I'm going to graph P times Q, right? If I do 0 tests, I get how much revenue? 0, right? Right? If I'm not doing a test on anybody, nobody's going to pay me any money, right? If I send Deb a bill for a bill and she's like, I didn't do a test, why are you sending me a bill, right? She's going to be, I'm not going to pay that. So I get 0. Right? If I do 1, I get 50. If I do 10, I get 500. If I do 1,000, I get 50,000. So what does that look like in terms of a line? It goes up and to the right, right? And what's its slope? So in this case, 50 cubed, right? So what's our slope? 50, right? It's going to go up by 50. For each test, it's going to go up by 50. So that means the slope is 50. All right. So go back to my example here. I'm running out of space. I'm going to shrink this down just a bit. You guys can, yeah, you guys can still read that, right? So profit is going to equal revenue minus total cost. Profit is equal to revenue, total revenue, minus total cost. I'll write that down in a minute. So if I do 0 visits, my total cost is $100,000 and I have 0 revenue. So I have a loss of $100,000. I'm just going to copy that down.
Are you on Excel?
Say again?
Are you on Excel? Because we can't see it.
Can't see it? I thought I had the share going. All right, hang on. All right, can you see it now?
Yes.
Okay. So I forget where we were. You saw the revenue, right? So profit. Okay. So at a volume of 0, we're losing $100,000. Why? Because we have 0 revenue and $100,000 in costs. At 1 visit, we have $50 in revenue and $110 in costs. So as we go along, right, we're making more revenue. We also have an increasing amount of costs, right? Costs are going up at the same time that revenue is going up. Why is that? What's the connection? What drives revenue? The reason that they're both going up, right, is variable costs are going up and revenue is going up. Both of them are driven by volume, right? Both revenue, both total variable cost and total revenue are both driven by volume. Fixed cost is independent of volume. This is going to be an important point later, right? Variable cost and revenue under a fee-for-service model are both driven by volume. Okay, so as volume increases, revenues increase, but so does total cost. But as volume increases, average total cost is decreasing. And so we can see that there's a point we cross somewhere between 1,000 and 10,000 where profit goes from negative to positive. That crossing point between losing money and gaining money is called the break-even point. So we want to find the break-even volume in this case. How many visits do we need to do in order to break even? So we don't know what that is just yet. We're going to figure it out. Might not get to it today. All right. So we're back on the video. Good. So we're going to lay these two things. Let me start by saying. So what I said was, I'm going to profit, I'm going to represent with pi. I'm not sure why we do that, but in economics and finance, we use pi, the symbol pi for profit. So profit is equal to total revenue minus total cost. Okay, so this is an important formula for you to remember. Profit is total revenue minus total cost. Total revenue is price times quantity. Total cost is fixed cost plus variable cost times quantity. And it's important to run that negative sign through when you do this. So total cost, profit is total revenue minus total cost. Total revenue is price times quantity. Price meaning the price that you charge for your services. Fixed cost, and then total cost is fixed cost plus variable cost times quantity. So if we were going to represent this on a graph, how would we graph, let's refresh, how do we graph total cost? We're going to start with fixed costs, right? and that's a horizontal line. And I like to draw it in as a dotted line because it's kind of not really there. But what that tells you is that fixed cost amount is your y-intercept, right? That's the point at which the total cost line crosses the y-axis. So that's your mx plus b. B is the y-intercept, right? And then the mx part is the variable cost portion. And so we have fixed cost that we have to pay regardless of our volume. And then we have, going up from fixed cost, we add on our variable cost, total variable cost, on top of the fixed cost to get our total cost. That's our cost curve. We already did that one. And what about our revenue curve? Well, we set our revenue curve a second ago, right? If we do 0 visits, Deb doesn't want to pay us anything. But if she comes in for a visit, she'll pay $50, whatever it was we said we would do, right? This is our slope, our variable cost per unit. So if Deb doesn't want to pay anything when she gets 0 visits, that means our revenue starts at the origin, right? That's the word for the point where the X and Y axis is crossed. It's called the origin. And it goes up from there. That's our total revenue. And that's the revenue per unit. So the slope is the revenue per unit. So in our example, the variable cost per unit is 10. The revenue per unit is 50. And so the total cost curve gets a head start over the revenue curve because we've got a fixed cost that we have to pay for first. So it kind of gets to get running. We start the race and the fixed cost gets to, gets a $100,000 or whatever it was, $100,000 head start on revenue. So it gets out in front, $100,000. The good thing about this is the variable cost goes up at $10 per unit, whereas the revenues go up at $50 per unit. So the revenue is running much, much faster than the variable cost is. So the variable cost is like a turtle, right? It gets a head start, but it's a turtle. It's kind of going very slowly, right? And the revenue is like a jackrabbit. It just, run, right? Real fast. So it rises, right? At least that's true in a functional business, right? Your revenue per unit has to go up faster than your cost per unit does. Otherwise, you don't have a business. Right? You just have a loss maker. Okay. So, so the point at which the total revenue line crosses the total cost line is the point where total revenue is equal to total cost. This is the break-even volume, BE, break-even volume. Break-even volume. So if we can figure out what that, so we know visually these two things are equal at this point. So at whatever the break-even volume is, the total cost is equal to the total revenue because the lines are crossing each other. When we're to the left of the break-even volume, total costs are bigger than total. That's my reminder to wrap up. All right. I'll stop on this thought. We'll pick up with break-even volume next time. To the left of break-even volume, you can see the total cost line is higher than the revenue line, right? So at this volume, we have costs of this much and revenues of this much. This is a loss, right? If I'm spending more than I'm bringing in, then that's a loss. To the right of the break-even volume, at this, whatever this volume is, let's call that V1 and this V2. At V2, I have revenues of this much and costs of this much. And so this is my profit because revenue is bigger than cost. Okay? So then break even is that point where the loss, the costs are equal to the revenue, so I have zero profit. So we'll get into that next time. All right, stop there for today. All right, so Tuesday, we will hopefully finish up chapter 5. And so homework would be due the following class, so Thursday. All right, gang, have a great weekend, and I will see you soon.